recording of a lecture that I'm going to give at EPFL Lausanne next week for the Aerial Robotics course. And so the real lecture is coming up soon, but at least here I will have a nice opportunity to record it even better than on place. So let's get started. So the presentation's name is called Introduction to the Crazyflie. As I said, it's a lecture for the Aerial Robotics course for EPFL. And my name is Kimberly McGuire. Today is the 3rd of April 2023. So yeah, the Crazyflie, what is it? Well, it's this little thing right here. And yeah, and I will actually explain to you everything like the 101 needs you for it to fly, but also what its capabilities are in terms of autonomy. That is all what I'm going to explain in this lecture. And if you would say like, yeah, for instance, like, yeah, this is such a small drone, why would it even be able to do anything at all, right? It's like very tiny, has a very small microprocessor. But then I give to you, how about a bee? How is a bee able to even fly around? Have you any idea how many neurons a bee has? But it has a very small amount of computational capabilities, and it's still able to explore a full field of flowers, remember where it was, communicate that to its peers. So yeah, that is pretty much my argumentation against that you cannot do anything on these small drones. And I will explain to you in this presentation what are all the capabilities possible. First of all, I'm from Bitcraze, which is the company who makes the Crazyflie. So it's a hardware company, and we're currently located in Sweden, Malmö, just across the bridge of Copenhagen. And these are all the team members: Tobias, Marcus, Christopher, Arno, Barbara, and Kimberly, me. Perhaps a little bit of a history. The history of Bitcraze, that it kind of started as a hobby project with the Crazyflie 1, which you can see a picture of this right here. It became actually so successful that they started a company in 2011 to start producing the Crazyflie on large scale. And of course, now the years has gone by. The company is now about 12 years old right now. We had our 10th anniversary a few years ago. And now we're at the Crazyflie 2.x. So who uses the Crazyflie actually? Of course, in the beginning it was more hackers and hobbyists. But now it's a lot of researchers that use the Crazyflie for their research. I was one of them, for instance, but you can see a video of a research compilation of the last couple of years of all the awesome things that researchers have done with the Crazyflie. Show designers, here's a Crazyflie show with about 20 plus Crazyflies. I'm not sure if you're able to see it very nicely, but let me give you a close-up. Where we flew with 20 plus Crazyflies in collaboration with the show company called Colmod. So that was pretty cool. We don't design shows ourselves, but others do. And of course, educators. A lot of educators use the Crazyflie for their courses, robotic courses, control courses. So that means is that you, as students, use the Crazyflie as well. So yeah, let's kind of dig into the Crazyflie and what is required for it to be able to fly at all and fly autonomously. I'm going to, during this presentation, I'm going to give you all kinds of tips and tricks, and of course give you kind of an overview of the full ecosystem, what is necessary to fly, so then you will be all equipped for using this for the upcoming obstacle course. So let's take a look at the ecosystem right here. So 3 things to keep in mind if you want to fly with a Crazyflie, which is first of course the quadcopter. Shouldn't forget that. And second of all is positioning, and you have all kinds of different ones. And the third one is communication, either with each other but here in this presentation I'm mostly going to talk about communication from a central computer. So let's first look into the quadcopter, shall we? So the Crazyflie, yeah, it's as you see a quad rotor, which means it has 4 motors right here, and it also has a control board that the legs are also attached to, and has a 1-cell LiPo battery, 7 minutes flight time. I by chance have here actually a battery with a little bit more capacity, and in total is about 24 grams, and that really depends on what you put on it. So yeah, the hardware. It has an STM32F4 autopilot. That's the autopilot microprocessor, and an NRF51 microprocessor, which is meant for the communication, and also it has an inertial measurement unit. You can kind of see the relative location here, although it's perhaps not that much use for you, but then at least you know which elements or which components you're looking at. And here's kind of like a framework of what each of these components do. Like I said, the STM is mostly for the main autopilot, which has all the controllers, the state estimators, perhaps some autonomy on board of that as well, but it handles mostly the stable flights. It controls directly the motors, and it also communicates directly with the expansion decks that I'm going to tell a bit about later. The IMU is on there, but of course you also have the the NRF chip and the STM chip that constantly communicate with each other, because the NRF chip is the one that actually is directly communicating with the computer. And also it handles the... So, inertial measurement unit, what is it exactly? I'm not sure if you already knew this from your courses, but here's just kind of like a quick preview. It has accelerometers, it has a gyroscope. Accelerometers is of course the measurement of acceleration, x, y, and z, and gyroscope is not the direct attitude angles, but it's the attitude rate angles, like yaw rate, pitch rate, roll rate. And it also has a pressure sensor as well, although by default it's actually turned off on the Crazyflie, but it's good to know at least that it's on there. And what makes the Crazyflie perhaps so special is that we actually use expansion deck to enhance its capabilities, either in sensing, computational power, etc., or to add, for instance, capabilities to input to use it for a different positioning system. And of course, I'm going to talk mostly about these expansion decks, which are the multiranger and the flowdeck, but more on that later. I will kind of show you first of how you can actually, guess like here is right the multiranger, here's the flowdeck, and if you get the Crazyflie the first time, if it wasn't used before, you might just don't get it with the expansion decks, so then you can you can remove the expansion decks like here, and then you can add it for something else, like something for, like, you know, maybe something like an LED deck for nice colors. This is then a lighthouse positioning deck that I'm going to explain later. That is a positioning system. But yeah, that is all you need to know for now. It makes a nice modular design of the Crazyflie. Next up, communication. So what is necessary to communicate with the Crazyflie? So we have also part of our ecosystem some client software, which consists of a client which allows you to visualize some things on the Crazyflie, even control it, but mostly to read out data, set some parameters. Is run on Python, which is in the backend. One other thing that is also very important to know, don't have one right here. Yes, that is a Crazy radio, which is very important for you to have. I have one here on my computer, but it's an extra one. And definitely for your course, you're going to need to have one to make it communicate directly with the computer. It doesn't mean that you don't need it at all. Like, we have mobile clients that you can use it to communicate with by Bluetooth. The latency is pretty big though, but at least if you just want to have a quick tryout and just see if it flies, you're able to kind of download the Crazyflie app on your mobile phone if you want. So yes, like I said, communication. So the Crazy Radio PA, as I already showed you right here, it's called the Crazy Radio PA. And it's the protocol it actually uses to communicate with the Crazyflie is called the Crazy Radio Real-Time Protocol, CRTP. Also, a good thing to know is that you need to know the unique URI of your Crazyflie, which is quite important, especially if the more people of you are going to fly the Crazyflie at the same time. So that means is that there are going to be 4 parts of this URI. First of all, the radio, the medium. You can also communicate by USB, a bit difficult to fly though, but you can for instance also add more crazy radios to the same computer. The channel, the communication speed, so here's 2 megabytes per second, and the address, which is as you can see, kind of an hexadecimal number right here. It is kind of also possible to communicate with multiple Crazyflies at the same time, although perhaps not super interesting for you, but you just have to make sure that you have a different address, and yeah, perhaps also kind of think about the channel as well. Okay, so the Crazyflie client is important to know about as well. So if you have Python installed on your computer, it's supported from 3.7, Python version 3.7 and up. Then the only thing that you need to do in your terminal is pip3 or pip install cfclient. And also you would need to kind of give it access to your USB device, the crazy radio that I just showed. Your computer needs to have access to that. So you can find the installation instructions right here to look back on that, because you have different instructions for Windows and different instructions for Ubuntu or Linux. Alright, so let's start with a hands-on, of course. So I already have a cfclient open here, and I now want it to communicate with my Crazyflie. I've got the address right here. I don't have an E7, 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 E7 as you see, because that's a bit dangerous. We never have that in the Crazyflie. And I'm just going to turn it on. There's a small button right here. If you can see, right here. It's a bit tiny, so perhaps just be a bit careful. So now it turns on. Just be careful of the battery. And then I press scan, and then it's able to find my radio or my Crazyflie right there. So I connect to it, and then you can see, of course, like the results of the IMU. So yeah, so that is kind of like what you can see at least. So just a kind of a quick explanation. So this is of course the attitude estimate. So as you can see, it's not a rate, but you can kind of see like, you know, what's in which, like how the pitch is and how the roll is and everything, just like in a normal airplane, let's say. You can also have some information about the actual X, Y, and Z, but we're going to also kind of show that later. So that is all we're going to show for now, but I'll come back to this later. Alright, one moment. Yes. Okay, next up, positioning. What is positioning? What kind of type of positioning systems are out there, or at least what the Crazyflie is able to support. So you'll have all kinds of different positioning types. You're perhaps more familiar with the motion capture system, which use reflective markers. These cameras or mocap cameras, they emit infrared light, and these reflective markers kind of bounce them back. And this, based on those images, it's able to determine the estimate of the Crazyflie, albeit on an off-board computer. So it still would need to communicate its position back to the Crazyflie with a Crazy Radio PA. Alright, next up is then the local positioning system, which is based on ultra-wideband beacons, which is range-based. As I perhaps also showed you in the big show video before, that was also using ultra-wideband, and it has also a capability of having more range. Yeah, so, and that is also pretty cool. They can have ranges between 200 meters between the anchor and the beacon. The lighthouse system, I actually have one right here. I'm not sure if I'm able to show that on next Monday's or Tuesday's presentation, but you can see one lighthouse system right here, which is based on the virtual reality system by HTC Vive or Steam VR, which we made a deck that's able to use those light sweeps from the lighthouse beacons, or lighthouse base stations they call them. And then of course relative positioning, the flowdeck, which is a bit special of course, because now it's actually using an onboard sensor in order to determine its position. And I will go a little bit more into that. So if you look at the flowdeck hardware, let me just very quickly show you a bit of a close-up of that. You'll see a range sensor right here. You see a optical flow sensor right here, and with that is able to determine velocity. And how is it able to determine velocity? I will kind of show you on the next slide. Oh yeah, by the way, I forgot to mention relative versus global positioning. All the other three ones that I've mentioned before, these are all global positioning systems. Means is that they all have a common coordinate system in order to determine the Crazyflie's position. But the flow deck has relative positioning, so wherever you start the Crazyflie, that is where the zero position is. So that's the important difference between relative versus global positioning. Just good to know. Alright, so flow and height is not velocity, so how does it actually get velocity from those two values? There's this simple formula that we use in the firmware to get velocity, which is height times field of view times flow divided by pixel width and the sample time. And this all is used in a... Oh yeah, I forgot to mention also, of course, if you rotate with the gyroscope, then you see flow and you're actually standing still. So it also kind of takes away that factor as well. And this is then used in a measurement model, which is then used in the extended Kalman filter, which puts out the state estimate in both velocity x, y, and z estimate, or a position x, y, and z estimate. In this presentation, I'm not going to go into the extended Kalman filter. You can either look at videos that I've done the previous years, or I'm sure that in the course there are a couple of presentations about this particular thing as well. But at least it's good to know that it's used to calculate the state estimate. So yes, let's go back to the cfclient, because this is actually a nice opportunity to show you how, for instance, you can set up some logging where you can check out how actually you're able to get some of these data in there as well. So let's see, let me just, I'm not sure, I have stabilizers, so that is indeed the yaw, pitch and roll, but we can already see that on the flight tab, so I'm not super interested in those. So I'm going to start up a logging configuration, which I'm not sure if you're able to see. Let me just go show you on the slides very quick. So what I want to do is I want to start a new category. I'm going to call it blah. I'm going to create a config. I want to like position, for instance. And then you see all these logging variables, which you also, by the way, can find on our website. We have documentation for each of these variables as well. Which one do I want? I might want to have something in the sense of state estimates. Yes, there you go. And I would like to check out the velocity in X and Y direction. So this is the blocking pyramid. Maybe I want to have it a bit quicker. There we go. Let's go back to the cfclient. And now, as you can see, I can calculate blah pos. And then you can see, if I move the Crazyflie around, you see the resulting velocity based on the flow deck. Must say that you have to have it a bit higher in order for it to react nicely. So let me just, yeah, that looks way better. Yeah, also this is kind of a white table, so maybe not the best texture table there is, but yeah. So let's put it back down, disconnect, and back to the slides. All right, so we talked about the Crazyflie itself, we talked about positioning, we talked about communication, but is it already able to fly? Are you able to fly? Well, not exactly. Well, there's some things that you would need to kind of understand about the Crazyflie a little bit first. So yeah, the Crazyflie is an unstable system. And if you talk about quadcopter dynamics, which I'm pretty sure there are already enough lectures out there that explain a little bit more, or enough videos on YouTube. But basically, if the motors are rotating, the propellers are rotating, it produces a certain lift because of the shape, and that results in a certain resulting force. But, of course, if you have some propellers or some motors rotate slower than the others, then you will have, of course, that you will have a roll or a pitch determined on which propeller is exactly where. And then if you pitch or you roll, you will have a linear acceleration to a certain location. And this is kind of where it becomes tricky, because a quadcopter is an unstable system by definition. So you will actually, if you don't have a positioning system that's able to detect that it's moving, then you will always have drift. So, yes. So let's kind of dig into it a little bit closer. So you will have, of course, sensors on the Crazyflie. And based on those sensors, if you think about the Crazyflie as kind of a black box, you will have motor output which reacts to the world and give feedback back to the sensors. And a little bit more detailed is you have sensor data that's sent to a state estimator, which in this case is an extended Kalman filter. Then that state estimates are fed into the state controller, which are, like, we have several controllers, but I think you're mostly going to use the PID controller, which there are plenty of videos out there that explains to you what a PID controller is, and I think in this course you will get a lecture about that as well. And if you get commands from the state controller, commands that is sent to some power distribution. For instance, you want to have a certain attitude that sends it, okay, which motor needs to do what. And of course you need some kind of reference to give to the state controller, and that is a commander. And that actually sets a reference, or we call it a set point, to the state controller, so the state controller can try to match the state with the set point. All right, so let's do another hands-on, I would say. Let let's go back to the cfclient. I need to first get a deck on this. Make sure that the battery doesn't, like the top deck is also meant to keep the batteries in place. Just be careful and of course turn it off, don't leave it on like I do. Just make sure that those pins, that you don't bend them, especially if they have these long pins. If you bend them, it's a bit more difficult to replace and add decks. Like, yeah, so just make sure that you don't put it on the wrong way. So now we have a, now is the, at least the battery is nice and secure. Okay, so now I'm going to move it over to the floor, and now I'm going to see if we can kind of turn it on. I think you can still see the Crazyflie, and then in the cfclient we do connect. Awesome, and now we want to kind of like look at the flight controller. The XYZ position seems to be okay. Yeah, we already checked out the flow deck with the VX and VY state estimate, so I'm pretty confident that we can just go ahead and fly. So you have these commander-based flight control buttons right here. So this is great for just testing out if your Crazyflie still works, or if your flow deck, or if your expansion decks are still working. I'm just going to press take off right here. There we go. So let's have a little bit of a close-up here. So you can kind of see it flying, and it's based now flying on the flow deck, so it's a bit dodgy. Not dodgy, I mean. It's kind of going back and forth. I think that's normal, but you can also kind of decide to, for instance, tune down the PED controller. We also have a nice tab for that. I guess good to know is not to place the hand underneath the Crazyflie like this, because that's what happens. Of course you can make a nice filter for that, but just to be careful that you don't put the ranging, yeah, let's say you don't put your hand underneath the ranging sensor, because it actually uses that for a height estimate, and suddenly it thinks, oh, I'm way too low, I want to be at 1 meter. So yeah, so that's why this nice crash is a nice demonstration for that. Alright, back to the slides. So I kind of explained to you how to make it fly, how to make it stably fly, or stable-ish, excuse me. But I haven't really told you anything about autonomy, because it's nice if it's able to fly at one spot, but what about the rest? Like what are you going to be able to do with it when you're going to prepare for the obstacle avoidance course? I mean the final competition that you're going to participate with your project. Well, that is of course very important, and I kind of want to show you, for instance, an example of my own PhD work a few years ago, where I had about 8 of these, or 6 of these Crazyflies with a flow deck, multiranger, fly fully autonomously in a building floor with empty rooms, and they had to kind of explore the room and come back to the initial position of where they started. So just to kind of as a demonstration, this definitely can be done. So, but I will explain how you're able to get autonomy on these Crazyflies after the break. See you in a minute. So yeah, I'm back. Just had to grab a little bit of water, and this break slide, which will happen in the real lecture as well, is just perfect for that. So let's get back into it. So, second hour, we're going to start with a very, very basic question. So, what is a robot exactly? Perhaps anybody in the audience will know. Now there's no audience, so I'm just going to tell it for you. A robot has sensors, it has actuators, controllers, and that's kind of all the things that I've explained to you before. But what is currently lacking in this list right here? Behavior. And behavior is very important because that kind of also makes the robot a robot. And what about a quadcopter? Is a quadcopter also a robot? Huh? Well, that's why we're here. It's an Aerial Robotics course. Of course it's a robot. But, yeah, so how does nature actually do that? We're not going to simulate all the neurons of a small bee. We're not going to make a small flapping wing MEV. But we can kind of still distill perhaps the, how do you say, philosophy from bio-inspired flight of bees. Like, we know it's possible, so therefore it's also possible on very small quadcopters. Especially a quadcopter that's technically 10, 20 times the size of a bee. I guess you're definitely familiar with, how do you call it, the car autonomy levels, right? So a car autonomy level is always says like how much is a human in the loop, how much does a human is able to take over control whenever something goes wrong, or fully autonomous, I think that's level 10. A human doesn't have to do anything at all, not even monitoring. So this is like for this quadcopter, of course, it's a much smaller product, it's much safer, but also the human in the loop is currently not really the concern, so we're already kind of assuming some type of full autonomy. So I have this kind of nice abbreviation as a mnemonic device to kind of show you the steps of at least what's going to be useful for you for the competition, let's say. The obstacle avoidance competition. So first of all, stability. I've already explained how you can do that. You have to that you're able to maintain the attitude, maintain the height, and stay still at one spot. So that is very important to do, and I already explained enough of that in the first hour. Second is T, translation. You're able to trust that your Crazyflie or your quadcopter is able to react upon set points or velocity commands or position commands from go from A to B or make a round or whatsoever. So that is all important things to, that is a very good baseline for your autonomy. Of course, avoidance, especially in the competition that you're going to participate. You have to avoid stuff. And if you crash against a wall or crash against an object, you're going to fall, and then it's pretty useless. You have, of course, drones out there that are able to also withstand obstacles or crashes, so that is, of course, also a thing. But the Crazyflie, for sure, cannot really easily recover from a crash. So A, avoidance. And then B, step. Purpose. So after you avoid all the things or all the walls, you need to go somewhere with a purpose. And that's kind of very important because, or else you just have a quadcopter that's able to very well avoid people or avoid things, and for crashes. But what is then actually the point of this autonomy? Like, you want to perhaps go somewhere, go to a certain room, find some people. So that is P for purpose. So let's look at translation, since we already talked about stabilization. So in the Crazyflie ecosystem of the cfclient, I already showed you the cfclient before, which is the one right here. But that's not what I'm going to talk about. I'm actually going to talk about the backend of the cfclient, which is a Python-based Crazyflie Python library, which is quite handy because you're not restricted by what the cfclient can do. You can actually write your own Python script from scratch. So how do we achieve translation of movement with the cflib? So you have then the Python script, you import the cflib in there. We're going to go through code a little bit later in this presentation. Then you will use the motion commander class that, for instance, that gives like a simple takeoff command, forward command, sideways, turn or circle, whatsoever. And then that generates set points that communicates that directly with a fixed rate to the Crazyflie. And I think also at least if you have one crazy radio and one Crazyflie, that's about 450 packets per second. So that is quite a lot. Oh yeah, also good to mention, as I said before, all the stabilizer modules that I mentioned, those are actually happening on board of the Crazyflie. So that's why the set points can be a little bit more high level, like go to 1 meter, go forward with a half a meter per second. And then actually the PID controllers already take care of that from position all the way to attitude level. Alright, let's take a look at the motion commander class, which is a class that's part of the Crazyflie Python library. So you see here the motion commander class where you put in the Crazyflie instance and the default height, which is by default about 30 centimeters, but of course you can kind of change that as you like. Then you have a couple of these functions that you can find, like going front, back, left, right, down, up, turning, turn left, turn right, circle left, circle right. You also have a couple of start functions as well, because all these functions that I just mentioned here are blocking functions, means is that the function will actually block the rest of the code until it has been executed. And sometimes you don't want to do that. Sometimes you just want to do things or measure things while you're moving. So that's why anything like the start, back, and left, right, down, up, if there's a start underscore front or start underscore back, then it's a non-blocking function, a non-blocking motion function. And of course, like the start linear motion one is the one that you're probably going to use eventually in your competition as well, among others. So that is just something that you can kind of add the velocity in body fixed axis and then yaw rate. To kind of go back, we have API documentation of the motion commander. So if you're kind of like lost and if you don't remember it after this, it should be all on the website if you go to the URL right here. So yeah, this is another time for another hands-on. This time we're going to look into the code. Alright, so this is not the code I want. I want to go to perhaps like a motion commander example, which I think should be, this is the cflib library. There you go. So in examples, Autonomy, motion commander. And then you have licenses and things like that. Then you have, so this is the motion commander demo. I'm not sure if you're able to see it nice, so I'll just make it a little bit bigger. And here you see all the kind of the imports that you have to do. So this is the motion commander import, the URI that you have to input, and then a sync class where you sync up with the Crazyflie based on the URI, which you can either, like, if you want to cheat, you can kind of change the URI here, or you can do it in the environment where you run the Python script, which I will go into show in a minute. Actually, I'm going to perhaps cheat a little bit here because I'm actually in Windows and I kind of forgot how to set an environment variable. But don't do what I'm doing right now. Oops. Luckily, I know my URI by heart. But technically, if you're in Ubuntu, so like it's just a matter of, for instance, saying cflib URI is like this radio thingy right here. And I think a PowerShell should be like set environment variables, but just want to make sure that it actually detects my Crazyflie. Alright, yeah, so let's look at this kind of a sync Crazyflie class, the motion commander that I kind of just showed you right here. And these, once you go into the motion commander, it will actually start, one of the entering functions of the motion commander is the takeoff function. So it will actually start flying from here point on. If you don't want that, you should probably comment it out. But yeah, just to make you aware. And then there's a whole set of functions that the motion commander demo has here. I don't want to show all of them because that's going to be a bit of a pain. So I'm just going to just do the forward and back part. And the up and down, yeah, like, you know, it goes up and down. It pretty much stands for itself. And perhaps, yeah, so like some velocity set points, so that I will just comment out all the rest. And once you get out of the motion commander instance, the with statement of Python, it will also automatically land. So you will see that in a second. Alright. So Crazyflie right here. Let's have it point towards the ground again. Make sure that the battery is nice and tight. Okay, and then we go ends in this terminal. I already have the Python environment on, and then I say Python. So since I'm in Windows, it's just regular Python, but for Ubuntu it's Python 3. Examples, Autonomy, and motion commander demo. And make sure that you save, or else it's going to do a lot more damage. There you go. So going forward, bit backwards, just in time, then sideways, and going back to the same location, and then a land. So that's pretty simple, right? So now we're kind of achieved translation with the Crazyflie. How about avoidance? Well, of course, as you can see, and I've already, yeah, how you can spoil the surprise a little bit, because I already added a, yeah, how do you call it? I already added a multiranger to the Crazyflie already. So yeah, so that already spoils the next part. You need a multiranger or a camera or something, at least that's able to observe the environment then looking downwards. Because if you have the flow deck, you cannot really do that much avoidance, because it's only looking downwards to determine its own velocity. So it's pretty blind. So you need it to make it unblind. You want, like, this is multiranger. You can kind of compare that, for instance, to a, yeah, how do you call it, like an maybe a LiDAR or so, but it only has 4 ranges. So let me just kind of go into the details right here. Of course, you would like to get the values within the cflib itself. It has 5 of these range sensors, also up if that's necessary. Now technically you can also grab the bottom range lens sensor as well if you want, in case you have to kind of detect if you're flying about something. So these are all important to know. And these range sensors, which are infrared light based, by the way, they can measure theoretically up to 4 meters, but that is very dependent on the environment. And you also need to be careful with direct sunlight. Like last year, when I gave the lecture also in person, there was a window on top, and that made that activated the top sensor, and of course I had a land function based on the top sensor that made it constantly go down. So that was a bit tricky. But yeah, the demo effect, you always have that. But just make sure that you're good, that you're careful with direct sunlight. Alright, so yeah, the multiranger push demo is an interesting one to kind of look at. And that's also kind of the first inclusion of a state machine. The motion demo, the motion commander demo that I showed before, that is just, it executes the forward, backwards, the sideways, and after that it just lands, and it's, yeah, that's it. But a state machine, that's more done in a while loop. And within the while loop, you may have to make sure that you also have access to the sensors, and this time the multiranger. So you have here the motion commander part right here. So that's you're really familiar with that. And then you also add a with statement of the multiranger. So that also enables you to get the multiranger data. And what you do, so like this is perhaps a little bit small, but the state machine, which is kind of like, you know, just a collection of actions and transitions. And here, for instance, the actions is just to hover stilly until a multiranger sees something, and then the other part is to move in the opposite direction until the path, of course, is clear. And this part of the code, it just yeah, let's say it has a different, of course, action. If the multiranger is on the right, you move to the left. If it's on the front, you move to the back. That is what all these if statements here are doing. And then you use this motion commander start linear motion, what I've told you before, which gives a body fixed velocity in x-y direction. Of course, you don't want it to go up. Yeah, so that is also kind of important to know. You are able to give it a yaw rate, which I'm going to show in a minute, but that is kind of optional. It's 0 by default. Okay, so we kind of already looked through the code, but let's go to VS Code, back to VS Code anyway, so at least you can know where you can find it. So this is the push demo. It's exactly the same as I showed you before. I'm going to cheat a little again with me not being able to remember how to set environment variables in Windows, which is completely my own mistake. Alright. And then we're just going to pretty much do the same thing. So I'm going to turn the Crazyflie off. So it's pointing into that direction. Not necessarily important for this demo, but it will be for some demos afterwards. Alright, and now I don't want to do the motion commander, of course. I want to go to multiranger, and then multiranger, the push demo. So you have a couple more examples. You can play around with it if you want. There's some pretty cool, like the point cloud one. Yeah, so I'm just going to go to the bigger picture here so you can more clearly see what's going to happen. So now the Crazyflie is going to take off. And what I'm now going to show you is that I'm able to move it with my hands based on the multiranger. That's pretty cool, right? You can also make it take off a little bit higher, but that's dependent on like how you initialize the motion commander. But this is already pretty cool. So you can kind of have an idea of what you can already easily do with the motion commander this way. Alright, so now I'm going to make it land again. Easy like that. So yeah, that was kind of like a small demo, perhaps not the most exciting part, but you know, you already got something flying, something that's reacting on sensors, so got pretty far. But how about more complex behavior, right? Because you can sure do a little bit more exciting than the push demo, but that is maybe a little bit more challenging. So like the Crazyflie is small, it's pretty safe. You can pretty much just code something, try it out, and it will crash, but it's pretty sturdy. But it kind of is pretty, it's going to be really annoying if it constantly crashes. You don't really want that. You don't want to constantly replace the propellers or the motor guards. And that's, in terms of development, it's not going to be that great of let's say development process. So let's go back to what I did during my PhD work a long time ago. You saw all those Crazyflies flying around. The most important part of that control, let's say, of that behavior was wall following behavior. And that was kind of the most important element of the swarm gradient bug algorithm, which was part of my last experiments for my research, and which I based also the Science Robotics paper on. And I took a couple of extra steps in order to go to the final experimental phase. So that is, of course, I didn't have the full algorithm right from the start. There were definitely some development steps that I took in between. And what is important here to notice is that first I did it in simulation. So yeah, I used Argos, which was like for a swarm simulator, and Gazebo is a mostly common used one in ROS. But simulation is actually quite part of your development process to be able to code in more complex behavior for your Crazyflie or any robot on the matter. So yeah, and simulation just in general, there's some multiple options out there. So you have general robotics simulators like Gazebo, Webots. I'm going to explain a bit later. Then you also have simulators that are more focused on realistic vision rendering. From NVIDIA they have their own robotics simulator. You have AirSim, which is also a realistic vision simulator. And then you also have a couple of these simulators that are more based on swarms. Perhaps the physics is not super accurate, or perhaps the vision is not super accurate, but they are very fast and they're able to kind of able to handle multiple entities at the same time. So here I'm going to explain about this simulator that you're going to use during your course. It's from Cyberrobotics, and they created Webots, which is an open source simulator, and they're a spin-off of EPFL. They're right across the corner of the faculty. And then you see here a random model of the Crazyflie, which looks pretty close to the Crazyflie. You have a collision model, which is just a cylinder. You kind of want to keep the collision model as simple as possible, or else your simulator is going to be way too slow. Then you have sensors like the multiranger that has been implemented there, although you don't see the render model of the sensors. You have propeller model of how much thrust is being generated based on the RPMs of the motors. And then you also have the controller that controls the behavior, the stability, and also eventually the behavior of the robot itself. So let's take a look at Webots, shall we? Of course, I have that already running right here. And you see the Crazyflie running here. So now currently it has a very simple controller, but we're going to look at it a little bit closer later. So now I will make it go and take off. So yeah, that is kind of like the push demo. Perhaps here you can also use your the keyboard to kind of make it control a little bit, make it turn. So, and you also have a nice camera, although you're not going to use the camera yourself probably, but at least you can able to see that. And if you want to see the multiranger, that is completely fine as well. If you go to view and optional rendering, You can make it show the lighter, no, not lighter ray paths, but scan the distance raised. There you go. So if you go a bit more closer, there you go. All right. Okay, so back to the wall following in simulation that I explained before as what I did in my PhD. I use simulation to fine-tune the wall following up to a standard that was, yeah, let's say doable. Let's go back to the slide. So here's kind of a state machine for wall following. So pretty much what it does is it goes to, if the front range of the, it will go forward first, and if the front range is too close to the wall, it will start turning into the corner, trying to align with the wall and follow along the wall until it hits a corner, or it detects if it's going around the corner. So you can kind of see the things right here. And like I said before, I use simulation heavily in order to kind of fine-tune this full process. So let's go back to Webots. And let's take a look at the controller. I open the robot right here. You can make an edit of the Crazyflie. So this is all what it all was using. You can kind of take a look at it at your own pace or in the controller file that your course is providing you. Right now I turn a certain part off. But that was actually the wall following demo that I'm now going to enable right here. So, yes, where am I? So this is kind of like based on something that I already written, like a separate file. And this is just kind of like enabling the state machine of that. So let's just close this and see what the... Yeah, so it's now trying to align with the wall. It's following the wall. It's like, oh, it's missing it, so let's try to find it again. I'm not sure if you're able to... Let's see if I'm able to kind of zoom in for you. Yeah, nice thing is here you can also, on the bottom here, you can kind of see the state that is being done. Oh, it lost the walls, trying to find it, then it found it again. Alright, so it followed the wall all the way. I'm going to stop this this simulation, go back to the slides. Yeah, so this is kind of how you can see how your design process is going to be. So as you saw, I actually imported a separate class or separate function that was called wall following. And that was actually on purpose, because then you can use the same code for both the cflib and Webots at the same time. No, not at the same time, but you can iterate between them. Let's say you can first try out your complex behavior in Webots first. Then it's like, oh, it works well. Let's try it out in the Crazyflie Python library on the real Crazyflie. Oh, maybe something has to be tuned a little bit better. Perhaps go back to the Crazyflie, the simulated Crazyflie, just to make sure that you're not breaking anything by constantly trying it out on the real platform. So in this way you can just constantly iterate and adjust the actual wanted state machine that you want, and then the Webots wrapper and the cflib wrapper just makes it easier to send the commands to either the simulated Crazyflie or the real Crazyflie. So yeah, what are the differences between parameter wall following from simulation versus real? Because of course I want to show this on the real Crazyflie. Perhaps, like, you know, there was also at one point that you have to measure or indicate what the angle is. So the angle buffer had to kind of change. The wall distance, the wall following distance to reference to the wall, that is something that I had to kind of pitch for if you compare it to, for instance, like the simulated one and the real one. Also pay special attention to the axis. Are the axes the same as simulation and the real Crazyflie? They are not. The pitch is negative, and you also really have to mind the units, like in what unit do you get the range meters in, like, or is it millimeters, millimeters? Yeah, should be millimeters. And also I found a bug. You need to perhaps also for the real Crazyflie negate the yaw, just plus to add a minus to the yaw before you send it to the Crazyflie if you use a start linear motion function, which shouldn't be the case, but just be aware and make sure that your wrapper around the cflib or your wrapper around Webots are able to take care of that for you. So nothing of that is in the state machine functions. All right, so now I've kind of tuned my wall following in simulation. Let's see if it works in real. So let's first go to VS Code. Yes, VS Code, and then I have something called multiranger follower. Yes, so this is a little bit more complex, but we have it now currently part of the Crazyflie Python library, so you can kind of check it out yourself. So I have a sync Crazyflie module, I have a motion commander, I have a multiranger, and I also have a logger. Because next to the multiranger values, I also had to get an extra value, namely the current yaw. So yeah, and then then you get the multiranger. You just make sure that that is all in the same units. And then I'm using exactly the same state machine that I was using in the simulator, Webots simulator, except for the exception of perhaps some first initialization values. For instance, like here I say I want it to be closer to the wall, for instance. Maybe I'm just going to change this to 5. Or the forward speed, I want it to be slower. This is all things that you can initialize within your wrapper, so that your state machine is not dependent on it. So yeah, let's see how this works. So same thing as before. Let me just restart my Crazyflie first and see what happens. Yes, Python, same as before. Maybe not multiranger, but multiranger. Did I do my nice hack? Like in the editing of this video, I will tell people not to do this, but I kind of have to. It's okay if you have Windows, it's fine. Nobody will look up you. Okay, so just make sure. And then I've got Python example /multiranger /wall following, which uses the exact same state machine as in the simulator. I'm just going to make it fly. So, alright. And then droidcam. Whee! I got an error, too many packets lost. That means there's something wrong. I did the URI wrong. Did I do that on purpose? Who knows? Nobody knows. But it's at least a good opportunity to show you what happens if you do that. If you put in the URI wrong. Alright, so that is all good. Then go back and play it again. And move to the big cam. Because of course we want to kind of show this. I'm going to follow it around so you can kind of see what happens. Yeah, it's almost the same behavior as in the simulation, as you can see. But that's pretty cool. I'll just make it land a little bit because we have limited time for this. Ah, I forgot to implement the height. I'll just take it, and if you flip it, it will also stop working as well. But you can also, the VS Code was also still on, so you could also done a Control-C, or you can put in like a keyboard space, make land, so that is, at least you have the power if you do it from the cflib. So, what are the pros and cons of offboard autonomy? The pros, obviously, it's quick development. You can easily switch between simulation and the real thing. Python is much more easier language to actually start out with. Yeah, of course. And it's easier to connect to other packages. You can connect it to ROS. You can go connect it to OpenCV, whatever you have a Python package for. So yeah, so that gives you a couple more nice capabilities. What it doesn't give you is enough communication bandwidth. So, sorry, I forgot to switch the slides. It doesn't give you communication bandwidth. And also there's a delay in communication, the speed of communication, like I said, 450 packets per one Crazyflie is fine. But what if you have a swarm of them? You have to kind of share this communication speed with all of them. And of course you need an external computer. And as you saw in the work with the swarm gradient bug algorithm, the computer was very far from the Crazyflies. Those were actually fully autonomous. Instead of, well, this one is of course fully autonomous, but what I mean is that they had full onboard autonomy. And that can be done with the app layer. This is beyond the scope of the Aerial Robotics lecture. Like, you don't necessarily have to do this. You don't have to make an app layer of your solution. That is not necessary. But you might get some extra points if you do. But yeah, let's see. I would be very impressed if you would be able to do. So what you can then do is you have your Python state machine, and once you're happy with it and once it's working as you want, you can start porting it to C code, exactly in the sense that I've done it. There is a way to, for instance, do Python on an embedded STM microprocessor platform, which is definitely something that we really want to implement at one point, but that is, yeah, we haven't gone so far yet. So maybe I'll be able to show that next year. But yeah, that is definitely, so then it's going to be even more simpler, but we don't have that for now. So okay, demo. Well, of course, going to show you why it's going to be so important to have app layer, especially if you want to have a swarm. Because I have 3 Crazyflies right here that have all the wall following app layer on board. So all of them have the app layer on board. I don't even have to use the Crazy Radio for it. So there's absolutely no communication with the computer whatsoever. I will actually get out my plug out my Crazy Radio at one point. So yeah, let's put them on the ground. I'll just make a nice row of them, and we can activate them one at a time. Because I'm not communicating with them by any way, I have another trick to kind of get them started, which is, yeah, the activating the top sensor. So of course I have to do that with the first one. And that one goes. Let's start that again. Yeah, so the reason why I just had a couple of crashes was because of this. Of course, the Crazyflie is not able to work that well, so yeah, that is a bit of a waste. But let's not have the battery cable around the propeller like this. So part of your checklist, just letting you know. And then let's put this one right back. See, all of them are okay. So let's try that again, shall we? Alright, so let's start with the first one. There it goes. I'll just make sure that it's trying to find the wall first. There you go. And the second. And the third. And let's follow them. And now you have 3 crazyflies flying in the same room. And if you don't believe me, I'll get this one out. No cheating. You see, they're still flying. Oh, getting close. They're not communicating with each other. In my research, they were actually communicating and avoiding each other based on their signal strength. Oh, because then that will happen. But that's fine. They're small and safe anyway. This one is still a trooper. Right, battery is a bit low. You can end. Alright. So that was exciting. Of course, everybody's familiar with the demo effect. So anything can go wrong. Make sure that you have a checklist before starting. Just still, if you compare onboard versus offboard, onboard you have more speed in terms of reaction to the sensors. Like the sensor doesn't have to be communicated to the computer first and back. There's no need for an offboard computer either. It's ideal for swarm communication, unless you want to have a lot of data from them. So, but you have potential to have even bigger swarms and fully autonomy in terms of you don't need to be so close to the computer. The communication with the computer is not super important. But of course, like offboard is easier development. You have more computational power with an offboard computer. But of course, the communication is limited. That is just how it is. But always, if you want to implement any complex behavior, start from an offboard control, offboard behavior first from a central computer. That's fine. Like in the development process is fine. But if you want to kind of make it deployable or more scalable for swarms, then onboard autonomy is more important. So let's go back to those autonomy levels. The STAP model, which doesn't exist actually. I just made it up actually. But still, you have stabilization, translation. I showed avoidance. I do have to say that the wall following avoidance, you might think, hey, so nice of you, Kim. You gave us the entire code to win the competition. No, I've seen your obstacle course. The wall following demo is going to be horrible on that. So unfortunately, you would need to kind of think of your own obstacle avoidance a little bit. But you can look at the current examples of how certain things have been done. So that's okay. But you still have to come up with your own algorithm. But there's one thing that I haven't really shown at all, which was also very important for my PhD work with the swarm gradient bug algorithm. But also for your eventual competition output is purpose. You need to have, if you want to have your Crazyflie, your Crazyflie needs to go somewhere with purpose. Like in my research, the case was that it's wanted to go into a certain direction, go back to the original location where I came from with camera footage, for instance. But perhaps in your case, you want to make sure that you don't crash, which is avoidance, of course, but you end up at a certain position to land, for instance. So that's a little bit less reactive. That means that you need to have some kind of higher level autonomy on top of your avoidance. So you have to kind of think a bit hierarchical right there. But this is, of course, all up to you, how you want to do that. So, yeah, I would like to thank you all for listening. My non-existing audience right here. But, of course, this lecture will be given next Tuesday. Hopefully all the demos will go well then. But that's all fine. So, I would like to thank you again for listening. And the website is www.bitcraze.io. And if you have any questions that your TAs are not able to answer, you can use our discussions format here, discussion.bitcraze.io. And of course, you can email us at contact@bitcraze.io or Kimberly@bitcraze.io if you have any questions about this lecture right here. Yeah, and good luck.